Gustavo Appignanesi. I'm from Bahía Blanca, Argentina, and I'm very happy to be here. I'm very grateful to Marcia and Paola, who are organizing this beautiful meeting. Okay, I'm going to talk on hydrophobic and hydrophilic surfaces and interfaces. That's the title put by Marcia, in fact, I think. But perhaps we could use also another one called water, one simple molecule, and two interaction demands. Or even one molecule, two ways of love, as we shall see that the way in what we're going to try to figure out the ways in which water relates to other systems. Okay, I wanted to begin with this prayer from St. Francis, who is in a book from Raúl Grijera, who many of you may know him. He passed away some time ago. He was one of the developers of SPC water model. He was from Argentina. He started his book with this prayer from St. Francis, which I think that in some way it tells us a very interesting message, since it is somehow, in some sense, it says, "Praised be you, my Lord, for Sister Water, who is very useful and humble and precious and pure." And I remarked sister water and humble, since I think that there's a message for us here. Since, you know, he remarks humble, humility in water. Water is simple, but we know that it presents a very complex behavior, a beautiful complex behavior. But he calls humble, simple, simplicity. And he also uses the word sister water, since, you know, St. Francis mastered humility himself. He was very humble, he was very simple, and in some sense he was what we can recognize him for his, the way he interacted with everything, with the world. He was a brother to everything. So here comes sister water, sorella water, aqua. And I think that in some sense this tells us that water is a simple system that behaves in a complex, beautiful way, and perhaps we should pay attention in the way in which it interacts with other systems. For St. Francis, interactions were everything. So, well, this is water molecules, just, this is not presenting, this is PDF. Well, it's okay. For me, I'm not, I'm keeping humble also, very simple in the presentation. So it's PDF, it's okay. It's just one oxygen, two hydrogens, and in science, austerity is a sign of beauty. And there's a mandate to look at simplicity into complexity. And in this sense, this is somehow related, since, you know, the simplicity that water presents does not prevent it to present a very complex behavior. So, in fact, it presents several structural, thermodynamic, and dynamic anomalies. I'm not going to talk a lot on this point, since I believe Marcia and Paola are going to do it much more better than me. So I'm going to only pinpoint a few things. So physics tells us to look for simplicity into complexity. And here we have a related question. How is it possible to bring complexity out of a simple molecule, out of a simple molecular structure? And here's what I wanted to put the focus: interactions. Interactions, the hydrogen bonds in water are very important. And we are going to pay attention to water interaction to see the way in which water interacts at first with itself, the different water molecules interact with each other, and then how it interacts with other systems. And we're going to try to look for some signatures of hydrophilicity. And in that sense, we're going to try to also develop a new measure of hydrophobicity, hydrophilicity. So these lessons are going to cover at first a brief study of water, of pure water, a few words also on glassy behavior, and then we're going to move to water solutions, then to the concept of hydrophobic interactions, and at the end, we're going to try to figure out the way in which water interacts with different systems and to try to look for the fingerprints of hydrophilicity. Here you have many reviews where you can look at this behavior, this complex behavior of water. This was a workshop in Buenos Aires with Marcia and Paola a few years ago, and from there we gathered two reviews. Okay, why is it relevant to study water at the supercool regime? Well, water presents a density anomaly, a maximum at 4 degrees Celsius. And it also presents a very complex behavior in these response functions. The thermodynamic functions, for example, the Cp, Kt, alpha, all the thermodynamic quantities show a complex behavior. And this behavior is more complex as you cool down water. So it is interesting to go to the supercool regime, since in some sense we are going to see that fluctuations are enhanced, and this behavior is more evident. But the problem is that homogeneous nucleation usually interferes, and that place is no man's land that is very difficult to study by means of experiments. And there are some, in the last year, there have been very beautiful and sophisticated experiments, but it has been a land more of computer simulations. Okay, this very briefly, a supercooled liquid or a glass. When you cool a liquid below the melting point, you can do it fast enough to avoid crystallization, and in that sense, you get a supercooled liquid that at some point is going to be very, very viscous. It's going to slow down very quickly, and then you're going to end at a glass. And the way or how fast you cool down, you are going to attain different kinds of glasses. And we're going to study this metastable state a bit more. I don't know if today or tomorrow, but anyway. The point is that the glassy water presents two different disordered solids, amorphous ices or gases, high density amorphous ice, HDA, and low density amorphous ice, LDA. There's also BHDA, and there are other things, but we're going to put the focus on these two ones. And when you look at the structure of these amorphous ices, you see that LDA is basically formed by molecules which are arranged tetrahedrally with a well-ordered first shell, and then you have a gap between the first and the second shell, which allows for an improvement of the hydrogen bond coordination. This does not happen in HDA, which is a high-density amorphous ice, since it is distorted, since a part of a fifth neighbor or more from the second shell have collapsed in the intershell gap and disturbed, in some sense, the first shell tetrahedral arrangement. This is the experimental GDR of LDA and HDA. And you see this is the first peak for, you have here this gap for low density amorphous ice. This is the second shell. You have a gap, but when you go to HDA, you have this interstitial region that is where you get these molecules that have, in some sense, perturbed. Sorry?
The labels are not inverted?
Inverted? No, this is the HDA here. You have a gap, and this is HDA, LDA.
But it looks like you should have more neighbors in the dotted lines.
In the dotted lines?
Yeah, it looks like you might have larger number of neighbors. The peak is much higher.
Well, this is an interesting point that when you look at what is, when you see the high density, this is the integration of the GDR. When you integrate the GDR, this is for the, only pay attention to the dashed lines here. This is LDA. LDA is the tetrahedral molecules. You have here the gap. And then, of course, you have the 4 neighbors here. But then the structure shows that you go down. And for HDA, what you have is that, okay, at first, you don't have this 4 neighbors here. You may have 3 neighbors. But you have these interstitials that at some point go up here, and you have a more dense structure. So dense or not dense, it depends on where you put the focus. Below 3.5 angstroms, yes, you're right. This is denser. But in the long run, the denser is the HDA one. Okay. Well, in supercooled water, the experiments were performed long ago by Angel and Speedy. And when they cooled down water, they observed very wild fluctuations in density at the molecular level. And somehow it seemed that the system was at the verge of a physical transformation. And here came this seminal paper by Poole, Shortino, Eastman, and Stanley that they proposed the 2-liquid scenario, that the existence of a water second critical point hidden in the supercooled regime. And they proposed that water had 2 different liquid phases that competed between them, and this density fluctuations arose precisely from the competition between these 2 species, which was what Angel and Speedy were seeing in the experiments. This was proposed long ago, 1922, and only around 2020, the first experiments were providing very important support for this theory. And the experiments had, the molecular simulation had also to wait to 2020 to see a confirmation of this theory for a model of water. Okay, the 2-liquid picture, in this sense, showed that the transition between the 2 amorphous ices extended into the supercooled regime in a Widdom's line that ended at some critical point that was very inaccessible, since this region was very difficult to accede by means of experiments. And again, similarly to these 2 ices, we would have LDL or LDA-like molecules, well-ordered tetrahedral molecules, and some more disordered HDL molecules. At this point, it was interesting to see whether we could have some kind of structural index and some parameter indicator that could produce two peak distributions, even at regions far from the critical point. And this is another form of seeing the differences between the two kinds of molecules. These are the low density. You see, you have here the gap. And in this is a configuration from a molecular simulation of a molecule in this case. And this is a simulation of a molecule which has covered the intershell region. So in some sense, it was interesting to look at this region and see whether this translational order could be used to provide some kind of parameter to discern between the two kinds of molecules. These neighbors here could even form what were called bifurcated hydrogen bonds, which in some sense lower the barrier to interchange hydrogen bonds between a water molecule and another one. Okay, there are plenty of structural indicators for water. Here we are going to pay attention to two of them. One is the local structure index. The two of them are, as I said before, are based on the translational order up to the second shell. And this one is the local structure index, which was proposed long ago by Shiratani and Sasai. And it calculated a parameter here that was precisely sensitive to the existence or not of a gap. When you calculate this quantity, if you have 4 first neighbors and a gap between the 4th and the 5th, you're going to have a high value for the index, and when this is not the case, you're going to have a very low value. This is the kind of distribution you get for this PCE water molecule at different temperatures. And some time ago, with Francesco Shortino, we decided to combine this kind of index with molecular, with potential energy minimizations to obtain what are the so-called inherent structures. Perhaps tomorrow we're going to speak about it a bit more. And when you combine this index with molecular simulations, you get a very neat bimodality with a kind of isospastic point here that separates the two kinds of structures. This was the first molecular index for water that showed such a neat change, such a neat bimodal distribution. In a similar way, Tanaka proposed another index, the zeta index, which basically introduces the notion of hydrogen bonds in the sense that it is also a difference between positions between neighbors of a central water molecule, but what it does is, well, you look at the last molecule hydrogen bonded to the central molecule, and the first that is not hydrogen bonded to it, and calculate the difference in distance between them. And this is this index. This is, for example, when you calculate it for TIP4P 2005 water molecule, and gives you some kind of bimodal distribution that you can deconvolute to get these two kinds of.
In this bimodal, one peak is related to this structure, HDL, and another one with the structure.
Yeah, here you have two peaks. Here you have to deconvolute them. For TIP4P, if you look for TIP5P, you get a much better distribution for Tanaka's index, but enhances bimodality a bit. But when you look at SPCE, it does not work as well as in TIP5P. The LSI, the other index, combined with the minimizations, you get the bimodality for all kinds of models we tried. Well, some ones we worked with another here, which was also by Roberto Carr in an ab initio model of water. Nielsen and co-workers used it in TIP4P, we use it in other water molecules, and in all cases, you get this kind of distributions. You get the 2 peaks. And this, the point is that this does not improve the situation, but it gets a conceptual advance since it considers hydrogen bond. And you know, interactions should matter, or at least that's what I saw in St. Francis prayer. So we decided to go directly to the bone, and then, okay, why not to focus explicitly on the interactions? And that's what we need when we developed a different new parameter, which was a new structural index, which was parameter-free, and was based on water interactions. And what we did was to look at to center at a given molecule, I, and we evaluate all its pairwise interactions with all other water molecules, and simple, we order them according to their intensity, and you pick the fourth of this, order in intensity, not in distance. This is when you do this and you combine it with potential energy minimizations, you get a very nice bimodality. This is, well, here we are showing the 2 cases, the real dynamic without minimizations and with the minimizations. In the two situations, you get 2 peaks, but it is neater for the minimizations. And this is the only indicator. If you look at the third, the first, the second, the third, the fifth, none of them gives you a 2-peak distribution. The only one that gives you a bimodality is the fourth one. So we call this index B4, and here is for 2 water molecules, SPCE and TIP4P 2005. From here, you can learn that there are 2 kinds of molecules, which we call T molecules, the ones for which B4I is lower than 12 kilojoules per mole at the inherent structures. These kinds of molecules have 4 strong linear hydrogen bonds, while you also have D molecules that are in this peak, which present a larger value before, and in some kind they have a distortion of one of the hydrogen bonds, since the second shell has collapsed in part towards the first one. This peak is somehow does not change much with temperature. And one interesting point is that when you calculate the index with the minimizations, you see this is in solid lines is when you use minimizations, in dashed lines when you are using the plain real dynamics, that is the configurations from the molecular dynamic simulations without minimizing. And you see that some population from here moves to the other peak when you minimize. This tells you that some of these configurations are inherently structured. The thermal energy is distorting the configuration, and you are seeing it as not ordered, while in fact the first shell is the first shell improves when you minimize. In other cases, you minimize and you cannot get anything else. This peak, some molecules stay at this position.
Are those peaks related to HDL and LDL?
That was our proposition, and this leads us to, well, you have to wait for another slide. But in this was the idea, and this is the fraction of the 2 kinds of species for SPCE at 1 bar. Well, this is at higher pressure, and this is for TIP4P 2005. And of course, this is the fraction of structure molecules, which is always the dominant fraction, and goes down as you, of course, as you increase temperature. This is the total potential energy in real dynamics, but this is when you minimize, you see that the D molecules do not move much. The peak which improves with the minimization is this one. The minimization brings some molecules from here to there, but these ones do not feel the minimizing procedure, and in these ones you improve a bit the hydrogen bonds or more. And this is the free energy profile that tells you basically the same, that this does not move much, and you improve here as you cool down. And well, this is for Marcia. So these were the radial distribution functions, oxygen for HDA and LDA, the experimental ones I showed you before. And this is the case what we get for the D and T molecules, which are very, very similar. As far as we know, this was the first time you could get such similarity, such kind of resemblance. And this is for, I think this is a SPC, and this is for T4P at the inherent structures and also the real dynamics, but it works in general better at the inherent structures. So in some, this is telling us that the liquid configurations could be thermally distorted relatives of the HDA and LDA, and there should be some kind of equilibrium between these two kinds of species in the supercooled liquid. Of course, this is qualitative. This is not a proof, but it's telling you that the configurations are indeed very, very similar. Here is what we showed before. This is the integration of the GDR for the HDA and LDA, and these are the relatives in the liquid. We find the D and T molecules, and you see again, they follow each other very closely. When you, here you are integrating this function. This is for the number of neighbors. Again, you see for T molecules, you have at 3 angstroms, you have 4 neighbors. In this case, you have lower. For the D molecule, you have around 3. But at some point, this is going to come up this curve, and it's going to be denser. It's not denser at the first shell. It's denser from the intershell region and beyond. Well, this is not very important. These are partial radial distribution functions. When you step at one kind of molecule and look at other molecules around them, well, you see that there's also some similarity with BHDA when you look at D and D, 2D molecules. Perhaps that's possible, but not more than that. The point is that T molecules, the structure molecules, are always dominant in our description. So when you are a T molecule, what you see around you are basically all T molecules. You have a low probability to see a destructor molecule around you. But when you are a D molecule, you are also going to be surrounded mostly by 3 T molecules. And this tells us to revisit, in some sense, the two-state picture by looking not on single molecule properties, but on 2 different local multimolecular arrangements. Thus, instead of 2 pure states, we presume that one should be in the presence of basically 1 pure state. It's the T state, but the other one is a mixed one. And here are total correlation functions. This function is basically the GDR, but if you don't have a structure, you don't have peaks here, you don't see clustering, but when you have peaks, you see clustering, and basically what you see is that there is certain tendency of the disordered molecules to be close to each other in some sense. But you also find the molecules that are completely isolated in the system. So when we move to the thermodynamic response functions, when you look at the specific heat, basically we calculate, this is what you have for the experimental system. And this is what you get for T and D molecules. And this is what you get for the complete system in the simulations. You see that the rise in the CP, here is basically the same thing, but the rise in the CP is due basically to the mixing term here of the two kinds of molecules, since both components behave as normal liquids. And the rise in the CP should be related to the interchange between the two kinds of molecules.
The excess of the...
Yes, yes, yes. And it's basically the part of the CP, the part of the volume is not important. What you see here, basically the internal energy and the volume expansion is not important. Well, this is the same, but for TIP4P 2005. And let me see. Okay. You again have some rise at low temperatures, and this is what we could get if we, instead of using the inherent structures, that is the minimizations, we use the real dynamics. If we use the real dynamics, you are not going to get the same kind of behavior as before, in which the T and D molecules were normal liquids, and the mixing between them was what led to the rise in the CP. And here, basically, all the behavior of the whole system was due to the disorder system. And this is because the system without the minimization is overestimating the D molecules. These molecules were not all disordered molecules. Some of them were ordered. So this tells you again that you need to use the minimization scheme.
The D particles, they are present even for higher temperature, where the two states are not, the idea of two states kind of...
Yes, the point that they are, they are very minority, since you have that this is SPC and TIP4P, and you have 350 here, Kelvin, and you still have high dominance of the T1s. That's why we moved to this mixed states, in the sense that, okay, again, you have T molecules that are basically surrounded by a sea of T molecules, and at some point you have some D. But the D ones are seeing basically other T, and perhaps one D. Thus, we decided to look at these environments, and to move from a single molecule level to a multimolecular level index I told you before. And then we decided to define different categories. This would be the D molecules, and the T1s would be divided in T0 when they have a D in the first neighbor shell, we have a T1 when they have a D at the second neighbor shells, and when you have all T1s up to the second shell, you're going to be T2. We expect that these ones are going to be more very, very structured and more frozen in some sense, and these are going to be the ones that move. When you, this is what you get when you look at the different kinds of molecules. When you have this would be the D and T we had before, and this would be the T2 and the other kinds. And when you look at how these different molecules behave in their dynamics, or how they survive in their state, in the sense that how long, for example, we measure this kind of defect correlation functions, that is how long a T molecule behaves as stays in a T state before it goes into a disordered one. And for all categories, we look at the point when they reach the level of defect you will have in the entire system. So the D1s are going to go from a high value to the defect fraction, the mean defect fraction of the system, and the others are going to increase towards this point. And you see that this is these time scales are relevant for glassy systems. I'm going to speak a bit I'm going to define, try to define these quantities in tomorrow. But basically what you see is that this T star is the time scale when a molecule basically feels that it is surrounded by other molecules, and it is caged by its neighbors, and at some point it becomes to break its cage and move in a diffusive way. And also you have this tau alpha, is the structural relaxation time in supercooled liquids. That is the time scale when basically all molecules have broken their cages. So all molecules have moved one interparticle distance. And this marks the relaxation of the whole system. And you see that the T0 and the T1 move very quickly to the mean defect time before T star, but the D and the T2 remain in their state at very, very long times. Thus, we decided that these two were behaving very similarly to these ones. That is, when you have a defect in your neighborhood, it is very probably that you're going to become a defect very quickly. So it does not matter if you are a defect or if you are a neighbor of a defect, you're going to change very quickly, and you are only going to remain structured if you have up to your second shell without the presence of any defect. And this is why we decided to define these ones as the structural states, and that the structural state would be a combination of the other ones. This is what we did here. You have the, oh, sorry, the
HDL, and I had HDL and LDL, you define by the presence, you differentiate by the presence of the D particle.
Mm-hmm.
Like in your, can you go back to the up picture? Like the D, T0, T1, all of them, they
All
have D.
in their neighborhood.
They have some D particles. How far you go to define, how far in the layering, because how
No,
far you go in the distance?
no, we stop here. We stop here at second neighbors. Since, the point is this. If you have a structure up to this neighborhood, you are not going to feel the defect you're going to feel to lose your structure at time scales that are very, very large, larger than the alpha structural relaxation time. So, but when you have a defect in this, within this neighborhood, you don't remain for much. Basically, if you're close to a defect, this defect is very close to your cage is going to wreck. But if your cage is preserved, in this sense, it's going you're going to remain as a structured molecule for very, very long times that are much larger than the relaxation time of the system. So we define the T2 molecules as the structured ones, and the others would be the unstructured. And when you look, this is what we get for the T2. This is what you see for the LSI, and the zeta index from Tanaka I showed you before. All of them show the same kind of behavior. You have, at very low temperatures, you have many structured molecules, and this goes down as you go up in temperature. Here for TIP4P 2005, the melting point is somewhere here. But you can go to higher temperatures. And this is also some result from machine learning calculation from Shortino and Martelli. And you see all of them work similarly in this region. This is the region where we expect that fluctuations are going to be maxima, since here you have the divergence in the CP and the KT. And we are in that region. This would be telling you that you would be close to the isofraction, which is called the Widom line. You have the highest competition between the two kinds of species, since you have an isofraction. You have the same kind of the two ones. So in this sense, we turned what was the original indicator was basically a defect detector, and in this sense, we are turning it into a water structural indicator that is working in a very interesting fashion. Okay, however, all of this is valid only for bulk water, and I was going to speak of water interacting with other systems. So I had to make some kind of introduction since our next step was, well, to move to a generic index that could be used in any other kind of situation. Since, basically, as far as I know, all structural parameters were defined for bulk water. And if you are using geometric presumptions to build it, when you are at an interface, the interface is changing the situation, and you cannot use geometric considerations to define an structural index. So we had an energetically based index, so it was interesting to try to see how it worked when you considered when you extended it to a non-bulk situation. Okay, so how are we in time?
If you are going to start something new, I suggest you start in the next.
Okay. So I was going to speak of supercooled grassy water. So sorry, sorry for the self-reference. I'm going to speak of more generic things in the next lessons, but I had to define some things I'm going to use at the end, in the last one. So in the next lesson, I'm going to speak a bit on supercooled water and supercooled liquids and gases, and then move to water solutions and to the hydrophobic interaction. Okay, thank you.